In this video, we're going to take a look at rotation. And you can see the objectives here on these next two slides. And there's a lot going on in this first section here. Most of it, however, is review from AP Physics 1. So first off, let's talk about the rotational variables. We have all of our variables in the linear sense when we talk about displacement, velocity, acceleration, and so on, and even force and energy. Well, we're going to have a whole new set of variables when we talk about rotational motion. And so when we look at motion of rotation, we have to apply these same laws, but we have to apply them in a slightly different sense. We saw this when we first looked at rotation, and we had to introduce these two new ideas of torque and rotational inertia. And so we come up with these new ways to express these ideas that don't really exist in the linear sense, but they only exist in the rotational sense. And so whenever we're dealing with rotation, we're talking about a rigid body. And when we use a rigid body, that's going to rotate as a unit, and everything's going to be locked together. There isn't going to be rotation within the object. And we also look at the rotation to be about a fixed axis. That axis is not going to change, nor is that axis going to move. These requirements exclude from consideration the sun, which has layers that spin within itself and rotate separately. And because of that, we get a bunch of other things happening, and so we're just going to ignore that altogether. We're just going to deal with rigid objects in this course. The axis that we rotate about, we're going to call the axis of rotation, and these two figures here below show us those reference lines. So it shows us where we're, the line that is going to rotate around that axis of rotation. So think that reference line, think of that as a handle that you're spinning around the axis of rotation. Obviously, we're going to use the measure of radians because that is dimensionless. We'll use RAD to signify that, and that is our rotational displacement or an angular displacement. And we know based from geometry that theta is equal to S over R, where S is the arc length or the portion of the circumference divided by the radius. So that's 2 pi r divided by r if we have a full revolution or 360 degrees, which gives us 2 pi radians. It is important not to reset theta back to 0 after a full rotation, because remember, if theta is our angular displacement, we want to continue to track that displacement after one full rotation. So we don't say that 720 degrees is equal to 360 or 0. And yes, in trig functions it is, but when we're dealing with an angular displacement, we want to know how much have we rotated. So we're going to continue to accumulate those radians. And we know all there is to know about the kinematics of rotation if we have the theta as a function of t for that object. So we can get all of our kinematic equations and anything from kinematics if we have a function of theta with respect to time, because knowing our relationships, take a derivative, we get our angular velocity, take another derivative, we get our angular acceleration, and that can tell us the entire story. Therefore, we will define angular displacement as delta theta, which is some final theta minus an initial theta. And another thing that we give for our notation here, or our reference, is we say that clocks are negative. And so what that means is that the clockwise rotation is a negative rotation. And the reason for this is using the right-hand rule. If you remember the right-hand rule of curling your right-hand fingers in the direction of the rotation, your thumb points in the direction of the angular velocity or the angular displacement. And so if you move your fingers in a clockwise rotation, you're pointing into the clock or into the board or into the paper or into the table, whatever you want to call it. And that is a negative direction. That's along the negative z-axis. So counterclockwise rotation is positive. And we've seen this all the way back to trig. When we open the angle from the positive x-axis, we open in a counterclockwise direction for positive angles. So it is important to remember that angular displacement in the counterclockwise direction is positive, and in the clockwise it is negative. So let's take a look at a disk that can rotate about its central axis like a merry-go-round, and we want to know which of the following pairs of values from its initial to final angular positions, respectively, give a negative angular displacement. So if we have an initial value of -3 radians, and then we go to a positive 5 radians, is that a positive displacement or negative displacement? And we see that only B and C are negative displacements, going from -3 to -7 and 7 to -3. Those are displacing in the negative direction. Well, moving along the kinematic ladder, we have angular velocity and instantaneous angular velocity. And so we, in AP Physics 1, said that angular velocity, at least the average omega, or the average angular velocity, is going to be the change in the angle over the change in time, or the angular displacement divided by time. Well, we're going to look at the average in that sense, but we're also going to look at the instantaneous angular velocity in using calculus, and that it's the derivative of the theta equation, and theta is a function of time. And if the body is rigid, these equations hold up for all points on the body. So it doesn't matter any point, whether we're near the axis of rotation or farthest away from the axis of rotation, all of this holds true. And the magnitude of the angular velocity we call the angular speed. So naturally, if we have a velocity, then a change in that over a time interval is going to give us an acceleration. So the angular acceleration, we use alpha to denote that. The average is going to be the change in the angular velocity over time, or delta omega over delta t. And the instantaneous angular velocity is once again going to be the derivative, or the time derivative, of the velocity function, the angular velocity function. And once again, if the body is rigid, these equations hold true. And we're going to use the right-hand rule again here. Now, this is a little different than the cross-product right-hand rule. This is where we're curling our fingers. We're not going to have orthogonal fingers. And so we use this to find the velocity and acceleration because they are vectors, and we can write the direction of these vectors. Now, displacement is also a vector, and so we can use the right-hand rule to determine the direction of the displacement vector as well. And if the body rotates around the vector, then the vector points along the axis of rotation. So our vectors that, or at least the direction of these vectors for the acceleration, velocity, and displacement are all going to be along the axis of rotation. Quickly here, we have a table 10-1, that gives us all of our linear equations transferred over to the angular equations. And all of these hold up if there is constant linear acceleration for the linear equations and constant angular acceleration for the angular equations. So these are basically just our kinematic equations translated into the rotational quantities. So a quick checkpoint here. In these four situations, the theta t is given. To which situations do the angular equations of table 10.1 apply? Well, like I said just a moment ago, we have to have constant angular acceleration. A, we have constant angular acceleration. B, we do not, because this is a cubic order. So two derivatives, we still have some dependency on t. And C, we do not have constant acceleration because this is actually a rational function. And D, we do have constant acceleration because the second derivative would be a constant 10. So we need to remember how to transfer back and forth between linear quantities and angular quantities, and everything differs by a factor of r. So to get from s to theta or theta to s, we have to use the factor of r. Remember, s is our arc length or our linear displacement, whereas theta is the angular displacement. Same thing with v. If we want to find the linear velocity, multiply omega by r. And we know that time, the time that it takes for one rotation, is going to equal 2 pi divided by omega, or 2 pi divided by the angular velocity. Likewise, we can find the tangential acceleration of something that's rotating to be alpha times r, but then there's also going to be the centripetal acceleration, or what we call the radial acceleration. And we can write that in terms of the angular velocity by finding, because we know centripetal acceleration is v squared over r, where v is our tangential velocity. Well, if we have our omega, now keep in mind this has to be rotating at a constant angular velocity. And so, and notice I use the term velocity, not angular speed, because angular velocity, we can be rotating at a constant angular velocity, whereas our tangential velocity would not be constant, okay? Because if we're moving in a circle with a constant speed, then we're rotating with a constant angular velocity, all right? And that might take a little while to let that sink in and understand what that means. But anyway, if we're trying to find our radial acceleration, well, we know that's v squared over r, which that turns into omega squared times r. And so anytime we have a rotating object, at any point, there are two different types of acceleration. There's tangential acceleration based on, are we increasing are we accelerating how fast we're spinning? And that would cause a tangential acceleration. But there's also a radial acceleration because we are moving in circular motion. Let's take a look at this question here. We have a cockroach that rides the rim of a rotating merry-go-round. If the angular speed of this system is constant, now this is angular speed, does the cockroach have radial acceleration, tangential acceleration? So if the angular speed is constant, so that means the angular acceleration is 0, then it will have angular acceleration, or excuse me, will have radial acceleration, but it will not have tangential acceleration because alpha is 0. Alpha times r gives us 0, so b would be 0 here. However, a, we would have a radial acceleration equal to omega squared times r. And if omega is decreasing, does the cockroach have radial acceleration and tangential acceleration? Well, it's still going to have radial acceleration, and yes, it will have tangential acceleration because we are decreasing omega. Therefore, alpha is going to be negative, and alpha times r would give us our tangential acceleration. Finally here, let's have a quick conversation about kinetic energy of rotation. And if every tiny little piece of mass is moving, then it's going to have energy. And it has energy based upon its motion, which we can calculate by 1/2 mv squared. And so if we add up all the kinetic energies of each tiny little infinitesimally small chunk of mass, and they all have different velocities, we add all these together, what ends up happening is we get the sum of really 1/2 m omega r, that quantity squared. And when we add up the 1/2 times the tiny little masses r squared, well, we know that this term right here, the sum of the mr squareds, that is the moment of inertia, and that is talking about our rotational inertia, and we use I to denote that. And so this is specific on an object shape, its distribution of mass, and all that. And we know that the objects that have their mass closer to the axis of rotation are easier to rotate than objects that have their mass farther away. And so that's why we call it inertia, because it's the resistance to change in motion. And so when we get something moving and it has energy, well, that's also going to depend upon its inertia. And so the moment of inertia is constant for a rigid object for any given axis of rotation. Now we have to make sure that we specify the axis of rotation because that determines what the moment of inertia will be. And so we write I as the sum of mr squareds. Now keep in mind, these are tiny little indexed m's and tiny little indexed r's, meaning we're adding up every little piece of this object. And so this is going to be kind of tabulated for us in tables, and for basic shapes, we'll have I calculated for us, and we can look that up when the time comes. But the key is the kinetic energy of a rotating object, and this is the rotational kinetic energy, is equal to 1/2 I omega squared. And we're going to use this equation for a finite set of rotating particles. Certain shapes, we're just not able to calculate I easily, so we won't be able to use this. Rotational inertia corresponds to how difficult it is to change the state of rotation, whether that's to speed it up, slow it down, or give it more energy or take energy away. Looking at figure 1011 here, we notice a solid rod that is rotating about two different axes of rotation. And we'll notice that it's very easy to rotate it in A than it is compared to B because the mass is distributed differently compared to the axis of rotation. And so with rotation, mass is only half of the story. The distribution or the distance the mass is from the axis of rotation is the other half. And so this example here shows that all three of these have the exact same moment of inertia because the mass times the radius squared gives us the same moment of inertia for these three.